Hello everyone. So we'll study chapter 2 part 3, the main property of the observed likelihood and its information matrix. So in the previous section we have studied that the observed likelihood is obtained by integrating out the joint density. So the observed likelihood should use this one. So observed likelihood is integrating out over this set, which is essentially same as integrating out over the missing part of the data. This is a joint density. Now we want to solve this, and then we want to take the partial derivative of this log likely function and set it to 0. And this one contains integration. So that's a little bit difficult to handle. So the computing the observed score function can be computationally challenging because the observed likelihood is an integral form. Okay. So the following theorem is probably the most important theorem in this class. Surprisingly, R.A. Fisher knew this already, and he didn't show that. Actually, he just said that, and then later it's kind of discovered by others. So anyway, the theorem basically states that the observed score function can be taken by the so this is what SCOM is the score function for the complete data, right? So this is the score function for theta with complete sample. So no missing, right? Observations. And so the observed score function can be obtained by taking the conditional expectation of the complete sample score function conditional on the observation, right? So observed data, observed part. Anyway, observed data. So that's the message, and then turns out that this is much easier to handle than the observed function. Okay, so to prove the theorem, we can directly use the definition. So eta. By the way, eta is the parameter. So this is the parameter for y, right? Density, and this is the parameter for the probability. So SCOM, as observed, that's what we want, and that is log of L observed eta. So that is L observed eta, and then take the partial derivative over L observed eta. and that is what? That is okay. So that is what is this? F y delta eta dy miss, right? Divided by F y delta eta dy miss. Actually, I can make it smaller. So then the numerator. Okay. So let's call this A. So let's carefully compute A. That you can actually change the order. Okay. So that turns out that you can write it as a ASCOM. So what is ASCOM? It's the scope function, right? Scope function corresponding to original data, joint density. So that is okay. So that oops, that's this one. So we want to use that. Use this relationship to here. Okay. So that basically provides ASCOM eta times density. Dy miss. Okay. And then B, and so that gives what? That gives, we can simplify as ASCOM, okay, F y delta eta y miss divided by S marginal density. Well, you can write it. Okay, so that basically what it does is ASCOM eta given the marginal density. I mean given the conditional. That's it. Because why? Because this guy, the denominator. Why? Because the denominator this guy b is equal to what? That's exactly the marginal density, which is the L observed, right? So that basically this is joint, this is marginal. So joint divided by marginal is conditional. So this is actually we can actually maybe write it one more time. So to be more rigorous, so you can write it as some joint divided by marginal is conditional. So conditional is something like this. Okay, right? So that is the that is conditional, and so that basically gives the what you want. So that basically proves that this is Scom Scom eta given y observed delta. Okay, that is that proves this result. Okay, so now consider the normal regression model. So that is a simple linear regression, normal regression model. And then scope function for beta and sigma square can be written as this. This is just a normal distribution, property of normal. And missing and random. Under missing and random, the mean scope function is just taking the conditional expectation of this. So this is actually taking the conditional expectation of beta and sigma square given observed data. So the observation is first R elements we observe. So conditional on, so okay, let me write it this way. So I equal to 1 to R expectation yi minus xi prime beta xi divided by sigma square given xi yi. So conditional on this, right? Conditional on x and yi, nothing random. So as everything is just fixed, and then I equal to r plus 1 to n, you have beta given sigma square given xi. Okay. So this part becomes this one. This part is 0. Why? Because expected value of yi given xi is xi beta, right? So xi beta minus xi beta is 0. So that provides the first result. Similarly, we can do the same thing and obtain. So it turns out that expectation of the square is just okay. Let me see if I can add a new page. Okay, so basically you have prime beta square divided by given observed. Okay, so that is I equal to 1 to R. You observe everything, so that's just the same square. If I equal to 1 to R plus 1 to n, then that is xi minus xi prime beta square given xi. So that turns out that that is expectations square, which is 0 plus variance. Variance is sigma square. So that's how you get this. Okay. So then solving this, you set it to 0. Set it to 0, you end up getting this one. So which it turns out that you can just simply ignoring the missing part of the sample. Okay. So the basically if you are interested in estimating the regression coefficient, and if you have a missing and random, then the partial response does not make any difference because this one is equal to 1. So no information. The same conclusion is this. So this is expression. This is an explanation in terms of the likelihood, and now we have an explanation in terms of the scope function. So in terms of the scope function, this is 0. Okay. So why? Because that is the Bartlett identity, right? First Bartlett identity. So that is which is theorem 2.3. So that's why so second term has no information. So that explains. So we have two explanation. One is in terms of the likelihood function. The other one is in terms of the scope function. Okay.